Uh, Dr. Arjun. Dr. Arjun Jain has been working in the, you can say it's a very impressive resume, you should say, actually, if you look around his experience. And he did his PhD from Max Planck, and that's where I met him first time when I was briefly there for a postdoc. And there he worked on computer graphics in the computer graphics department there at headed by Professor Hans-Peter Siedel. And he has been working on consistently human body pose estimation problem. He has also been participated to this one of the Tiano, if you have heard of it. It's the interesting ideas on autonomous driving and all. One of his, I think, some ideas are also companies were acquired, right, by the Mercedes,
right?
That he co-founded with his advisor. Then he came to, I think, India immediately after that, right?
Yes.
And he founded Fast Code AI, co-founded Fast Code AI, that he is still a chief scientist there. He joined IIT Bombay as an adjunct faculty. You joined as full faculty, I think, right? And then, no, adjunct only. And he is also, like, recently his 2 PhD students from there are graduating. One has gone to Max Planck for his postdoc. And then again, so the Fast Code AI was more on autonomous driving. Then he, of course, looked at the next big thing is drones. So he founded, and he's the CEO of UAVIO, which is a UAV based, basically a drone startup looking at various aspects of commercializing the drone services, including algorithmic, while he's still pursuing his publication, the publication-oriented research, I should say, with publishing in top conferences on human body estimation in autonomous navigation scenario in the wild setting for multi-human and really complex environment. So, and then he has also did at some point of time software engineering job also. He has worked at Yahoo. I think it's a very diverse resume, and he has a lot of experience of all kind. So I'm happy to, we are happy that he came here, and he'll take actually 2 invited lectures, one on autonomous driving and one on his core area of human body pose estimation, which will be scheduled tomorrow. So I would like to, without any delay, request him to take us through interesting slides and interesting content on what he has been doing at UAVIO. Thank you.
Thank you so much for that very kind introduction. I hope you can hear me at the back. Yeah, so it's very nice to give an in-person talk. I think this is the first talk I'm doing in person after COVID times. So let's try and keep this interactive. What I'm going to do is I'm going to talk about self-driving at scale and where are we headed. I'm going to show some of our work. I see Shubham here, who was part of some of our works at Mercedes-Benz. So without further ado, let me talk about, let me show you, what I'm going to talk about. So I'm going to start with some of our own works. I'm going to talk about a little bit of history. Then we're going to talk about the kind of autonomous agents. Then the future, what the cutting edge say, and this is mostly happening in companies due to various reasons. We'll talk about it. I'll talk about the data factory, the so-called data engine, about sensors and redundancy, how simulation is really essential to achieve self-driving. Finally, hardware on the edge, and when will we get there, right? The million-dollar question, when will we have autonomous vehicles? So I've been lucky. My company was acquired by Mercedes-Benz, and I've had the pleasure to work with, of course, Mercedes, now Volkswagen. I was with Apple's autonomous driving division in Cupertino, and Bosch is also one of our long-term clients. So I'm going to talk about interior of the car and also exterior of the car. So here is our line manager from that time, Volker Entenmann. And this is Paris Auto Show 2018. And this is when Mercedes, for the first time, launched a car with a camera inside the car. So behind the rear view mirror, there was a camera. And based on that, we realized some user interface kind of use cases. So for example, when you point to the screen here with your finger, the corresponding icon gets highlighted. Here you see that the passenger seat is already highlighted. So it's one click less because we know if it's the driver or the passenger, right? And then there were some, like gesture based use cases, some pose based use cases. For example, also when you take your hand, because we now have, the 3D position of the hand and the other joints inside the cockpit of the car, even when you take your hand to this touchpad. So Mercedes-Benz has a touchpad there. You can still do the same operations. So this was 2018. And then the next big launch was, in the S-Class, in the Maybach. And this is where we did full body. So here we also have cameras in the back. And based on the head position, the headrest automatically adjusts itself. So this is implicit, not explicit. So this is an explicit gesture where you can close the door. Similarly, this is again implicit, right? Because when you want to reach for the seatbelt presenter, you do this and it automatically presents. This is so one implicit, one explicit. So this is an explicit gesture and so on. So again, reading light, you just do a tap. I mean, this is, in my opinion, very useful because it's difficult to, find that button very easily. So this is already in production. You can buy it as the MBUX in the MBUX options, in the MBUX package. And this was CES 2020. So both front and rear cameras. We published a bunch of papers. Mercedes very generously funded our group at IIT Bombay. And then we moved on to, the exterior of the car. So here is Anurag, a student from IIT Bombay, and myself, and one of my companies, Axogyan, and my academic affiliation. And here what we did was we kind of came up with a fast way to do pedestrian detection so pedestrians and vulnerable roadside users. So vulnerable roadside users can also be bicyclists, people with prams, and so on, right? So the question that we want to answer today is, why could we do this only in 2018? And where are we headed from here? So the reason is, we've been trying to do this for a long time. For example, one of my advisors, Chris Bregler, has an old paper in 1998. This is my paper from 2010, where you see we're doing full body tracking, but it was never good enough for industry. And then AlexNet happened, and then it changed the whole game. I mean, only after deep learning, after AlexNet, it was these kind of techniques were good enough to be used in the industry, right? And by the way, let's try and keep this interactive. So if you have any questions, just raise your hand and we'll take it from there. So I know it's evening. I'm not going to bore you too much. I'm just going to give you a very quick history of autonomous driving. So this is not something that has just started today. There was this Eureka project, Prometheus, in Europe between 1987 and 1995, and Vita 2. So on the right that you see Vita 2 by Daimler-Benz, which could already drive successfully on highways without too much human intervention. And then, of course, most of you are aware with the DARPA challenge, which started in 2004. But maybe you do not know that all participants actually failed to finish this 150-mile off-road track the first time. And the main reason was that there was this stringent rule that there should be no driver or no human intervention at any level, right? So it had to be completely autonomous, and all of them failed. So then next year, in 2005, DARPA did this again. And this time, 5 teams managed to complete this off-road track without human intervention. And the interesting thing was, Velodyne wasn't supplier to all the teams. Anybody knows what is Velodyne? Anybody heard of Velodyne? Yeah? Yeah, perfect. So this was a LiDAR company. It was a startup at that time. And this is when Velodyne then raised a lot of money and became, the company that it is today. And then there was also this DARPA Urban Challenge in 2007. And it was an environment modeled after a typical urban scene, the kind that you see here. But it was, not a true urban scene in the sense you didn't really have live pedestrians. It was kind of a static world situation. And 6 teams managed to complete this event. Now, you can do autonomous driving in 2 ways. the ego only systems or connected systems. Ego only system means that the agent itself has all information and you do not assume help from other agents around itself. Connected systems are, where you can assume that others, so you have partial information, the agent has partial information, and observations from other agents are communicated to, to every other agent. But for today, we will focus only on ego only systems. And the reason, I guess, is obvious, because we cannot really trust connected systems, right? I mean, you need to be self-reliant and plan for the worst case. So we talk only about ego only systems. And then this is, I think, where the shift is happening today, mostly in the industry. So end-to-end versus modular. So you can do, again, autonomy either using end-to-end systems, which is the newer way to do things. And in an end-to-end system, in the ideal case, you assume that the signals such as the camera video and say the GPS information, so the sat-nav information is put into some giant network, some black box, and there is uncertainty propagation from sensing to action, and outputs are directly driving commands. For example, how much should you turn the steering wheel, how much should you press the brake or the accelerator, and so on. Right now, the modular systems are ones where you can break the the steps to achieve autonomy in these stages. So the first stage is perception, followed by scene representation and localization. Then comes prediction, so predicting where others will be. Then finally planning and decision making. What should my path be? So this is planning. And finally control. So how much should you steer the steering and so on, right? So I'll go over all these subsystems in a little bit more detail, and then we'll come back to the end-to-end or hybrid systems. Yeah. Radar, they dumped radar. LiDAR was dumped forever, but they dumped radar, yeah, last year in October. Perfect. Thanks. Yeah, we'll talk about all of that. So I have slides for all those things. All right. So, after a few slides, if I haven't answered your question, we'll come back to it. Any other questions? So I'll talk about Wave. I'll talk about Wabi. You've heard of Wabi? Yeah, we'll talk about all that. Yeah. All right. So let's talk about perception. So what is perception? The dictionary meaning of perception is the ability to see, hear, or become aware of something through the senses, right? So for example, in a sentence, you would say the normal limits of human perception. Now, perception is a very difficult task, and I want to show you using an example. So suppose this was the image. An autonomous agent driving on a road would need to know about all these moving objects. So things like the cars, static objects such as this traffic cone, road signs. So not just detect, but also recognize. Also overhead signs, traffic lights and their states, right? What state it is in? Is it in green or yellow or red? Lane markings, is it solid or broken? Road markings, it says halt here, it may say school ahead, curbs, crosswalks, and so on. You may also need to know about environment tags, such as are we in a residential area, are we in a tunnel, are we approaching a toll booth, etc. So there are so many things that we need to know about. And let's now focus on something very specific. So let's say we talk about only moving things on the road, right? So each subtask has additional subtasks. For example, object types. So for example, all these are supposed to be moving objects, though this is not moving anymore. It is under a collision state. There is a pedestrian, there's a biker, and these moving objects can look very different. Finally, you just don't detect the object, but you also have to know a little bit about the state. For example, the car, is the blinker on, which blinker is on, is the brake light on, is the parking light on, has it undergone collision, and so on. Now, so this is all from Karpathy's talk, by the way. People who haven't seen it should see it because he talks about other things which I don't. Now, perception has this long tail problem, meaning though you can solve for majority of the cases, the tail end, the ones where it becomes very difficult because each subtask, for example, car detection can already look so difficult. So all these are, say, cars, and all of them look very different. And finally, we are not okay with the 97% performance. Finally, we need a 6 sigma performance. We need like a 99.999 kind of an accuracy because this is a safety critical application. You cannot make a mistake. But this is, of course, after sensor fusion. It's not just from one sensor. There are multiple sensors, and so the hope is that the accuracy should get better when you do this sensor fusion. Also, you have tracking, so tracking also helps. So the long tail problem that I was talking about, what we want to do is we want to capture behavior of corner cases. But by definition, there are not so many of them in training data, right? For example, if you want to say get a distribution over human, say human driving behavior, then the most of the data that we would get is around the mean where the driving is normal. But if you want to get data for conservative, maybe old people are driving very conservatively, or aggressive, right? So where people are not driving well and driving very fast. So to get this kind of data is obviously difficult because these are corner cases by definition. Now, I want to elucidate, explain this using a very simple example. So traffic sign, you would think is perhaps the easiest class out there, right? Outside the car, because it's a planar object and so on. But there are challenges, and the challenges that it should be high accuracy. It should work without HD maps. There is a lot of data imbalance, and some rare signs have very few examples. And it should be a low latency, high accuracy system. And just to let you know, there may be 600 classes. So Germany has 600 different traffic signs. And the kind of data sets that we have, for some we have maybe 10,000 examples, but for some we have less than 30 examples. Yeah. And in real life, it becomes like this kind of a complicated system when you want to solve traffic sign recognition. And here, the use case was level 2, level 3, where we just display the detected sign on the dashboard so that the driver is aware. He doesn't have to search for the sign on the road, right? And here what we did was we have first a detector. Now a detector cannot do 600 classes, right? You cannot directly ask the detector to already classify it into so many. So we have a first level of classification from the detector. So it's a traffic sign detector, and it tells us the shape, right? It tells us if it's circular, triangular, or rectangular. So you get the bounding box. You then you may also need to do some OCR on it, because you would then put this crop inside another classifier, which would then be the fine-grained classifier. And finally, there is something called as parent association, because sometimes these signs appear in hierarchy, right? So something as trivial as traffic sign is already complicated. So you see where I'm going from here, right? So it's a really, really complicated engineering solution. So now let's talk about scene representation and localization. So here, what it means is we have done perception. So we now can identify things, and we then need to place all of them in a common coordinate space, right? So we may have different sensors, then we need to bring them all into a common representation, and also localize ourselves, meaning the car, in that world, right? So one way to do localization is using LiDAR. So when using LiDAR, what people do is, he was saying, they first map the entire neighborhood or the city, and then based on the current observation, they match it to the city, and then they can tell very accurately, centimeter level accuracy, where the car is, right? So you have a 3D scan of the entire city, for example, and then based on the current observation of your agent, you're able to tell where you are in the city. So you do something like ICP, iterative closest point, to localize, your car. Now, this is good, but this is expensive. Firstly, because LiDARs are expensive, and secondly, because you have to map the entire thing. So companies like Tesla, they're trying to do this using, only vision. So they have all these cameras, they can get 3D out of it by doing structure from motion. I'll come to you. And like you were saying, right? So Karpati says there are multiple reasons of ditching radar. One, because when there is a conflict between radar and vision, which one do you go with, right? So there has to be a third sensor to do this disambiguation. Secondly, what he also says is, so by the way, Karpati is the head of the director of AI at Tesla. And the second reason they ditched radar in October last year was because they wanted to bark down only one tree. So they had two different teams and they were both trying to solve, I mean, both teams were trying to solve the same problems, but using different measurements. So they said, okay, let's get rid of radar and let's see how far we can go with only vision. So does that answer your question a little bit? I mean, that's all they say. And if it's right or wrong, we don't know. So because I mean it's still just driver assist and they're not able to do like level 4 like what Waymo is able to do now in San Francisco and Phoenix. So this is an image from Waymo's representation, and this is the scene representation that I was talking about. So here you see that so here you see that all these purple boxes correspond to these vehicles. This basically tells that okay, it shouldn't. So this is basically maybe this line. This is your pedestrian, your speed limit. So everything in this one scene, right? So this is your scene representation and also localizing. And then this is where, your current lane and so on. So this was your second step. So we did perception. And after perception, we did this scene representation and localization. Yeah, go on. Yeah, good question. So they claim that even if you switch off the headlights, firstly you have headlights, so headlights illuminate the scene. Even if you switch off the headlights, it's pretty good because it has a high gain, their cameras. And even with things like the backlights, they're able to. So they say that the backlight is already enough. A few lux, like 10 lux or 5 lux, or even lesser than that, is enough to illuminate this. Yeah, go on. Yeah, good question. So there is a lot of post-processing happening after collection. So these people go manually clean. So there's a detector. You remove those things. So yes, you remove it manually. So no, not on the fly. I mean, you get that scan. Then there are data annotation teams. They remove the 3D points that correspond to that car. So I mean, but then there is like you have the car, but then you have other things, right? So hopefully you will get a good confidence and your thing will still stick. Yeah, and you can always do say car detection and remove that part from your ICP, right? So you can remove those points which correspond to that car. Yeah. No, that's a very good question. So I'll come to that. So Tesla has by now say 800 cars, actually more. 800 is an old figure. And whenever there is engagement, for example, whenever the user has to do some engagement, that is when they get the data back. So I'll talk about that in one of my slides. I agree with you. So that is why I'm not sure if vision only is going to solve the whole thing, but we'll see how far we go. Anything else? No, Uber had lidars. Yeah, I'll show you again a slide later on if we have the time, that is. So we should also. All right. Cool. Anything else? No. All right. So moving on. So we did perception and scene localization, right? So we did these two steps. Then there is prediction. So we need to predict where others will be. Why? Huh? No, but why do we need to predict where others will be? Let's say there are no people. We're talking about a highway. Actually, highway is where you need to do this prediction. No. Exactly. So the reason is that because look, there are, if you do the math, if you're traveling at 100 kmph, you would need maybe 100 to 150 meters to come to a stop if your maximum braking efficiency is say 5 meters per second square kind of a thing, right? So you need to predict. And if you think about it, on highway, the behavior is very well defined, right? Nobody will do any sudden movements on the highway. So if somebody is going straight, we are pretty certain that he will keep going straight. So you need to do this prediction step, meaning we need to predict where others will be so that we can plan around it. Because if you don't do that, we don't have enough time, right? You will then not be able to take the decision because then you don't have enough time to for this response. Does that make sense? Right. So here is an example where there's this cyclist, and I mean, you don't usually need it for cyclists, but here we're kind of predicting, okay, will it go straight? Will it turn right? Will it stop at the traffic light? And based on that, this car is going to decide what it will do. Will it go straight or will it stop? Yeah. Yeah, so all those are corner cases. I mean, if there is an accident, then maybe it will recognize things like, okay, there is a, there is some sirens or there is a cone, traffic cone. So it is recognizing all those things. Yeah, so there is always LiDAR, right? I mean, it will know in the long range that, okay, if it's a static thing, that it would know from a distance that, okay, there's something going on and you should stop. We'll take it offline. Yeah. Anything else? Otherwise, we'll not finish those. Cool. So finally, planning and decision making. So now what we've done is we have perceived, we've brought them into the same coordinate space. We in the same, and then we have done the prediction. And finally, before control, we want to do planning and decision making. We need to plan the route. And by the way, only this part is mostly machine learning, right? Rest of it is all deterministic algorithms. So for example, for planning and decision making, for say finding the path, you would use something like an A-star algorithm. So here you see that there is this cone, there is this thing. So it finds all these paths. Each path has a cost based on time, based on collision, based on is it taking me to the right goal and so on. So based on that, this path was chosen, and it does it in an update loop. It keeps doing it all the time. And based on that, this car successfully took a right turn. Okay. And finally, control. So control is when you want to execute the path from motion planning by giving relevant actuator commands. But there are errors, right? You have errors in translating the path because of say PID control, because of so many things. And this is where so I'll not talk about the details, but again, there are errors and you need to deal with them. So control is again a big topic, and also with autonomous flying, control is a big problem that we currently have because you're not able to model the physics of the environment perfectly. If you could do that, if you could model friction, then this was not a problem. So when you do PID control, there's a integration term, there's a derivative term, there are coefficients in front of it. So to find the values of those coefficients, and it assumes a linear function. So you may need to bring some non-linearity. So it's a very complex problem. So modular versus end-to-end, right? So modular, why do we want to do modular, or why most people, so Waymo is doing modular, or Tesla also has a kind of modular approach. So modular approach is easy because from an engineering point of view, it helps us divide tasks within a team and is more interpretable, right? Also, you can test these subsystem at the interfaces. Yeah. Secondly, hand-coded rules, priors, are easier to include in each model because they're all broken down. But what you have to give up is, each step of the process is performed in sequential modular silos, so they don't talk to each other. Stack has to be manually tuned for each introduced image. limited information shared across modules, and you rely on modules for each problem. For example, if you're doing the stop sign and if there is foliage, then you have to again change that module or add another module to it. So the end-to-end way to do it is you remove everything from the middle. You put a black box in there, maybe a giant neural network. So then what are the pros? I mean, it's simple. It's a single AI system, and it is really trained for the end task. In the modular thing, there are errors propagating from the beginning to the end. Here we are actually training it for the end task. But then what are the downsides? First, it's difficult to add priors and rules. How do you add priors and rules to a neural network? Say you want to give it a rule that okay, always be in the left lane and so on. It lacks interpretability more than the modular system, because here you're not able to test it at the interfaces, and it requires a lot of data, right? Because now it's this gigantic thing here. So this is Wave, what you were talking about, by Alex Kanda from Cambridge. And here they're kind of doing end-to-end deep learning with very little supervision. And they're able to they claim that they're able to train a system in less than 20 minutes. And after a little bit of training, after a little bit of engagement, this small car is now able to drive autonomously on the streets of London. Yeah. There's no product. So let's be clear about that. Yeah. Mm-hmm. What they're trying to do is this hybrid approach where you don't do everything modular and you try to do one or more things together. So I'll show you some papers related to that later. Any other questions? Right. So now let's talk about maybe the middle ground, the hybrid system, where you get your sensor data in, and you maybe do one or two steps together, and you do the rest of it like earlier. So here, for example, we're doing perception and prediction together. So the modular approach helps divide tasks within a team and is more interpretable, and you can add these hand-coded rules. But like I said, like everybody's in a silo, you're not optimizing for the end task. Each stack has to be manually tuned for each introduce this thing, right? So all these things that we've already described, and then there are these cascaded errors, because if there is a mistake early on, there is no way to fix it. So this is, in my opinion, very, very interesting work by Professor Raquel Ultrason from now from Wabi. So she recently raised $100 million and is backed by the bigwigs, Jeffrey Hinton, Jan LeCun. All these guys have put in a little bit of money. So it kind of validates. And what she did, so these are two recent papers. And what she's doing is, she's saying why. So let's try and do these two things together. Let's not do the whole thing together, but let's do these two things together. So she takes in the voxelized LiDAR and the raster map and route, and they're doing semantic occupancy forecasting. So they're doing these two things together. So what they're doing is they're directly predicting the occupancy grid, so where others will be in a grid, right? So they're kind of doing these two tasks together, and this is still safer and more interpretable than training end to end. And this bit is trainable end to end, and you have your motion planning, and finally the trajectory and the control, right? So I'm not going to, we don't have the time to go into details of these two papers, but people who are interested will share the slides. You should go into it. But I think this is one way to do things, and this is the approach that we have taken for our unmanned aerial vehicle company to achieve navigation. Though we don't really have to do forecasting in the sky as much, because you kind of assume a static world situation there. Now, classical words versus modern ML systems. You all know that the classical ML systems were like using these tools. So it was accessible, more accessible, and everybody had like everybody could just go and start using it. But then you could only do so much. And modern techniques, like modern deep learning techniques especially, is like building this factory. So it's not about simple tools anymore. You have to first build this factory, and then you can pipe a lot of products through it. And what does this factory look like? This factory looks like, something like this loop. So again, this is from Tesla, because they share it publicly. What we are doing, there is IP and customer rights involved. So we're not showing exactly our pipeline, but it's very similar. And so this is called the data engine. And what they are doing is, so you start with some bootstrap data, some small data set. You train your initial model. You already deploy it, right? So you deploy it, though you don't use it. And then based on your current measurements, you somehow identify if your model is right or wrong. So one thing you have to understand is there is no ground truth here, right? When it is deployed in real life, you don't know if it's performing correctly or not. But there are still ways of knowing what is important data, where this thing is failing. For example, one is disengagement. The other is consistency among sensors. The third is tracking, right? So based on all those, we collect more data samples. For example, maybe it fails in a tunnel scenario. So you then collect more data from the tunnel. You maybe give more weightage to these data samples. You label it, and then you retrain your model and you redeploy. So then you have to have over-the-air update possible, right? So that you can redeploy your model almost seamlessly, and then you keep doing the cycle. And the hope is that someday your model will be accurate enough when you can call your customer and tell them that, okay, do you want to buy our autonomous system now, right? So Volkswagen, by the way, one of our customers, is doing exactly the same thing. So there are cameras retrofitted already, which they're selling. They're not charging for the cameras yet, and we're basically doing this in Germany. Now, sensors. So these are the kind of sensors that autonomous agents use: vision, radar, lidar, GPS, ultrasonic. GPS also has problems of latency, right? The signal goes to the satellite, comes back. If you're moving at a speed, then there is uncertainty. You can then do real-time kinematics, where you have multiple GPS. You can triangulate between them. So there's a lot of complexity in each of these individually. But all these are important sensors that these companies use. Now, sensors. Talking about sensors, we should talk about sensors should be complementary and redundant. For example, if you have an infrared sensor in addition to a vision sensor, then maybe you have some additional information. Maybe they're complementary. Or lidar versus vision, then they're definitely complementary, right? Maybe places where lidar does well, your vision doesn't, and vice versa. So those are complementary. And you need redundancy, meaning you need to have redundancy in your system. So the biggest example of not having proper redundancy was this Boeing 737 MAX fiasco. So they did not have a proper redundancy, and I think many jets, like 3-4 of their jets, met with accidents. What they had were, so the angle of attack sensors. Anybody seen this Netflix documentary? Okay, awesome. So their angle of attack sensor, there were 2 angle of attack sensors on the tail, but you needed a third one to break the, so you should have a lot of redundancy in your system. All right. So now talking about the sensor setup comparison. So this is for you, right? So you were talking about Uber. So Uber totally had 10 cameras, 6 radars, so many ultrasonic, 1 lidar. So these were the total number of sensors Uber had. Google Koala has 5 lidars. Some of them are short range. This is Google proprietary lidars that they have. And then Tesla model has the least number of sensors. Why do you think Tesla has the least number of sensors? Sure, but there is a so do you think that is the only reason why Tesla has lesser number of sensors? Yeah, so that's the major reason, because you can buy a Tesla for $35,000. Yeah, $50,000 or $200,000, right? You would rather buy a Rolls Royce or something like that. So that is one of the biggest reasons why Tesla had to do this compromise. Yeah. So this is the kind of inference we did, right? So we kind of did some analysis and we found that Tesla Model S, it's reliable. So it has reliable environment perception only in standard self-driving use cases, and most corner cases are not manageable or with severe restrictions and no redundancy. So that's not a good thing, right? But there's a trade-off in terms of cost and the amount of sensors that you can put. Google Koala has very good near field due to the availability of this proprietary small range LiDAR by Google, and they use two different types of LiDAR. And finally, Google XC90 had problems with entering priority roads because it was missing these corner LiDARs in the front, and they had to rely only on radar for this special case of entering priority roads. All right. So, I mean, I'll not take too much of your time. I see it's already end of day. A lot of people are yawning. So let's try and, cut to the chase. So one of the major things that you need to do, like you were talking about, is simulation. So Carla is one of the simulators, an open source simulator. You can play with it. Waymo has done a lot of simulation. So, they have 25,000 cars running, virtual cars running 24/7 in their simulation. They've done more than 10 million miles per day, and totally they have more than 7 billion miles in simulation. But you don't usually do, say, perception using this simulation. You do everything else, right? So you remember the other 4 steps. You do all of that using simulation. But so Wabi here is kind of trying to change that. And what they're doing simulation back to the sensor. And when you do this simulation back to the sensor, you can do closed loop learning. What it means, you do a simulation, you render images, you train your model, you check where it fails, you go back, do your simulation again, especially for cases where your model fails, and you keep doing this training without any human intervention at all, right? So this is Wabi's reason why they raised $100 million, because they have a really, really good simulator. Yeah. Yeah, good question. So that is what they are solving. They're saying our simulation is so good and so photorealistic, and they're able to match this noise profile of the sensor so well that they're actually able to train it, and when they actually deploy it in the real world, it works. And if you look at current research, if you look at the kind of like synthetic data sets, and if you train with them, you can get to say 80-85% accuracy. Yeah. Yes. To model that, again, you may need real world data, by the way. Yeah. We're not developing in India. So there is a startup by these two, sorry? Swayat Robotics has not raised funding, but recently, yeah, exactly. Minus Zero raised $1.9 million, started by these two kids who just graduated from college, and they're trying to do it for India. But yeah, India, we have, like a different situation. You may argue that maybe it's easier to do it in India, right? I mean, it sounds weird, but because you don't need to know where lanes are, you don't need to know about the light, you don't need to know about traffic signs, and the speed is low. And all you need to do is you don't need to bump with the next car, right? That's all you need to do. Yeah, so you don't do prediction anymore. Yeah, but there are pros and cons. I mean, to be honest, that is, yeah. So we'll see where we go with it. Yeah, go on. Yeah, very good question. Very good question. So, so you do use audio for sirens. So that's the only place where they currently use audio. Yeah. Sorry. Yeah, we're far away from that. Yeah, we'll get to that when we actually get to level 4 and so on, right? So currently we're far away from it. Yeah. Yeah, so in the US, actually, GM, the expensive GM cars like the Cadillacs have this system already where they communicate with the car behind them. For example, in the US, when the weather is bad, you may have crashes with up to say 70, 100 vehicles, right, piling one behind the other. So in that case, if you communicate with the car behind you, then there is so much gain. But then again, different vendors have to talk to each other, they have to be standards, so on and so forth. So it's not really a reality yet. Yeah, but it's not, this is a safety critical application. You have to make sure that there is, it's like, so you may have heard about the 2015 Jeep hacks by some, so the Jeep car, the Cherokee or some of their models were hacked and then they were stranded by the road, right? So there are a lot of, and like GM has developed it, then others may need to buy from GM. How do, like, all these, so these open standards are coming, but they're not there yet. But yeah, at least for those kind of situations, uh, when vehicles talk to each other, it's a real boon. Yeah. Yeah. So RL based control, right? So it's a field in itself and it's nowhere close to, say, your PID control at present. So RL for control has been used for these weather balloons, helium balloons, for controlling the temperature in these data centers, but they're nowhere close to be used for, like these real time situations. Yeah. Because we know that we're failing there. So we want it to not fail the next time when you encounter such an example. So this is a standard technique, right? Yeah. It depends. We can do the math. Um, when I teach object detection, we do that. Like, we figured that you need to be able to detect a person, say, 35 pixel tall in a 2K image if you want a car going at 100 kmph to stop before hitting it, right? So this person is 100 meters away and there it's only 35 pixels. So, I mean, we can calculate that. I know. Yeah. I know. Yeah, so it's all very exciting. We'll see where we go. There's a Indian company, a friend of mine called Flow Mobility. So they're kind of trying to do a similar thing. So yeah, we'll see where we go. So it's an interesting times we live in, and yeah, especially in India, because I think IIIT Hyderabad is one of the very few institutions which, in collaboration with Intel, has created this data set. Right? Others, I mean, there's no other data set that I know of other than that data set in India. So data is, I think, the one of the biggest problems, and then of course funding and so on. Like, so this project that I was talking about with Bosch and Mercedes-Benz, that paper that I showed you, it was a failed project, and every month they were burning $300 million towards the end, right? So you see the kind of burn that goes into in building such these big systems. Any other questions? Yeah. Yeah, I think we'll be somewhere in the middle, right? Like you have to converge from both sides, because then if you have better data, then your algorithm needs, I mean, you don't need maybe a very good algorithm to solve this problem. So I think we'll converge somewhere in the middle. Yeah. Yeah, so I think this is where the revolution will come, right? So CVPR this year has this very interesting paper from, in my opinion, where they're doing depth and the quality is maybe as good as LiDAR in a self-supervised way. Have a look. Yeah. Cool. Anything else? Sorry. Yeah, and LiDAR. Good. Sensors like LiDAR, you would know there is an obstacle. Even if you cannot recognize it, you will at least know that, okay, you should stop. I mean, humans also have the same problem, right? So there's only so much you can do. Yeah. No, not true. In Phoenix, you can, like you can actually hail a self-driving car. In San Francisco, it's happening. In New York, it will happen. Yeah, but V2X is a topic in itself, and it's still, I mean, it'll take some time for V2X to, because this is a standard problem. It's not really a engineering problem. And I have a separate talk for that actually. So it is a complete thing in itself, but V2X is still, like out there. It's not going to happen anytime soon, in my opinion, at least a few years. Anything else? I mean, you have to come up with a self-supervised strategy. So the signal has to come from some place, and one of the hurdles can be, again, validation. For example, if you have only unsupervised data, no labels, then how do you validate your approach? But there are no hurdles as such. You just need to design better algorithms which give us the kind of accuracy that we're looking for. Yeah, but then you need LiDAR, which may be expensive. And if you may need multiple LiDAR. So anything else? All right. So if you want to build autonomous vehicles, you also need a testing facility. So Google has this one in Castle, California, which is 91 acres. ISC is building one. But yeah, like IIT Hyderabad, I know, is also building one, because our UAV startup is incubated by IIT Hyderabad. But yeah, I think more needs to be done. And I don't know of any, testing facilities which are this big. So a lot of, again, it's very capital intensive. Again, we did not speak about hardware, but hardware, so processing hardware, right, is again a major bottleneck. There are so many sensors, maybe 10 sensors, 8 sensors, each giving you maybe 2K, 4K images, or so many thousands of 3D points. And then you need to process all of them in real time, right? 30 milliseconds or so. And then, so there are, like, Tesla is building its own computer. NVIDIA has, is also building a big one. These are all teraops, because when you deploy your neural network, you quantize it. I mean, you can easily, or not very easily, but you can definitely, you usually, I mean, you start with these 32-bit floats, right? Which, when you train a model, your weights and your activations are all 32 bits, but then you're able to quantize it to 8 bits without any loss in accuracy, because loss in accuracy is not acceptable, right? I mean, we're already aiming for 99.999. So loss in accuracy is not acceptable, but still you can do, these unsigned char, let's say. So you can do calculations using just 0 to 255. These are a bunch of companies doing autonomous driving, and this last row is the most interesting for me because these are the new kids on the block. We already talked about Wabi and Wave, and then there is also Aurora, which is doing trucks, so self-driving for trucks, and Einride again is a company from Sweden doing the same thing. And I've been very lucky to be associated with 5 of these companies, so I've seen some of the things which are going on in here, but I would really also want to spend some time with these companies and see what they are doing. Yeah. I mean, in 2015 we had $3 billion in the bank, so money can do a lot of things. We'll see where Apple goes. Yeah, I mean, first when I was with them in 2015, we wanted to build the entire car. We wanted to redesign the seats, the leather, the everything. And then at some point we realized that maybe let's just stick to software. I was not there, by the way, at that time, but yeah, we'll see where Apple ends up. So it's not just the autonomous car. Once we have autonomous driving, there will be so many things, and there are so many things that are associated, and these are like companies, you can look at it later, which operate in different these things. And then this $1 million question, so like when will we get to true autonomy? Like when will we really have autonomous cars on the street? And this is from Professor Olson of I think University of Michigan. He also owns a self-driving company called May Mobility, and he came up with this graph. He says, so on the y-axis is miles per disengagement, how much a car can go without the driver having to take over, and on the x-axis is the year, and this blue line, this blue dotted line, is basically human level performance. So humans usually on an average meet with an accident every 10 to the power 8 miles, so every 100 million miles. Now currently there is disengagement at around 10 to the power 4 miles, and the progress since say 2005 has kind of been linear. So if we simply extrapolate it, we'll get to true autonomy in 2037, but this is pessimistic, right? We don't want to believe it, but maybe he's also saying that this is level 5. Level 5 is when a car can go everywhere. Level 4 is when a car can go to known places where there is a geofencing, when there is a known area. So hopefully we get to level 4 before here. And as we're already at level 3. Even in India you can buy cars with level 1 and level 2. So most new cars, Kia cars, MG cars have level 1 and level 2 kind of safety. And yeah, so this is the last slide for the day, and this is Tesla's urban and highway full autopilot. You can see that it's pretty impressive. It can do a bunch of things, but it's also always in the news. You may have heard that when doing the summon feature, so you can summon your car, and Tesla recently hit someone, hit actually a plane. Did you see that in the news? Yeah. So it hit a plane when it was being summoned. So I just don't understand how it really happened. So yeah, so that's all I have for today. Feel free to connect with me on LinkedIn. We have open positions in our company, UAVO. So I'll again advertise it tomorrow. I'll actually put up the job ad as well. And we're really looking for people like you. So if any of you are looking for a job, please consider applying. We'll start interviews next week. So yeah, we still have maybe some time for questions, or maybe you already want to, call it a day. So that's also fine.
Just send us the rejection list. We'll be happy to have. Okay, any questions, guys?
Yeah, go on. No, we're doing all metric. Yeah. So all these measurements, even vision measurements, you can always do calibration if you have an object of known size, and then you can get to metric. So we're all doing everything in metric. Yeah, I think we'll get there someday.
Any other question, guys? No? Okay, so I would like to thank the speaker. So tomorrow, the next talk will be morning at 11 o'clock, and the morning session will be in the KRG auditorium. Afternoon session will be in okay. So see you tomorrow. Thank you.